Thank you for joining Rumsey on our ongoing Locked In series hosted by our Rumsey specialists. My name is Sean Huber. I'm one of the Automation Systems Group Managers here at Rumsey. Today we're continuing to focus on the power side of our business with a presentation on state machine and motion control and why it's a must. So with that, I'd like to introduce Mike Persing. He's one of our motion control specialists here at Rumsey. Mike's been with Rumsey for just about 10 years, and besides just handling motion, he does tend to get into the middle of a lot of things with mechanical systems and drives and pretty much anything else that pertains to a successful solution for our customers. So with that, I would like to turn it over to you, Mike, and I'll let you get started.
All right, thank you, Sean. Good morning, everyone. Like Sean said, my name is Michael Persing. I'm one of the motion specialists over here at Rumsey. Here's my ugly mug. I've been doing this for about 25 years. Be 10 years in June coming up at Rumsey. Before that, program commissioning, design work, pharma equipment, and an OEM. And then previous to that, it was on the maintenance side of things. Quite often, because servos are mechanical as well, all my references, if anyone on here has interacted with me, if I need a reference for loads or moments or whatever, all those terms associated with motion, they come from the automotive world because they make basically machines that can operate for hundreds of thousands of miles, so they must be doing something right. So let's get into it. Maybe this isn't the best way to start it off, but what we're not going to talk about is when you refer to state machines, you may have heard of overarching philosophies or architectures for controlling the entire machine. There are several standards, one of them being the S88 model, usually used by process, was developed by the ISA. Again, it's a state machine, but not the topic of our conversation. I just wanted to make you aware of this. This is a method of control of getting the machine starting and running and holding and all these different steps. PACML, I believe, was built on top of S88, but to be more closely associated with discrete machines that are present in the automotive industry and it's applicable to packaging and so on and so forth. Again, a state machine, a state model, but for overarching and controlling, stopping, starting your machine. Combination of that, what Rockwell did was come up with Fitties Manager, put the two together, have steps running in the background. They call it Fitties Manager, sort of an integrated function call. Again, we're not going to get into it, but I just want you guys to be aware that of these three, I guess we'll call them two big organizations, and then Rockwell, they're all about a sort of a state machine for machine programming, so why don't we adopt that? The point of this presentation is to maybe abandon what I call bitbang, meaning just using bits to control your process, interlocking those bits, so on and so forth, chasing them around for troubleshooting. I mean, granted, once a code is vetted, troubleshooted, and working, there's multiple ways to skin the cat of sorts. And Bitbang, yes, can make machines run, so can state machine, but perhaps the state machine is a little bit easier for you and others to deal with, and also it's very conducive to motion. Why use a state machine? Specifically to discrete machines, is what my familiarity is with, not necessarily batch. They're interference machines. Things can crash. Bad things can happen. I mean, of course, in any machine, bad things can happen. But in a packaging machine, the idea is to keep things from crashing into each other. The state machine itself makes management of the sequences easier. And I'm just going to make these statements and then hopefully prove these statements throughout the presentation, or at least convince you at least to try it. A state machine can help with the ease of troubleshooting. The code can be self-documenting with states that use descriptive terms. Knowing what state the machine is, and rather than chasing bits, covered that before. And then following the logic can be easier from one troubleshooter slash programmer slash engineer to another. Another thing that a lot of people have run into, and I personally, Sean as well, as processors get faster and faster, or the big leap from, we'll say, PLC 5, SLCs, a traditional PLC, to Logic 5000, some old tricks with the way a PLC would scan through its code, then update outputs, so on and so forth, don't necessarily apply. Specifically, Logix 5000, the I/O is updated asynchronous to the program scan at some RPI or some rate. So some of those little tricks to manipulate with the PLC scan don't necessarily work. A state machine can help with that by keeping it in an orderly fashion. You have an existing machine, need to add a step, need to do some separate function, just insert a state within your code, rather than, if you saw on the previous screen with all the interlock bits and so on and so forth, rather than interlocking and so on, just add another step to your state. So what is a state machine? Now, granted, that first statement can be said about almost any program as a structured method of sequencing operations. Specifically, the big idea is it's centered around the equal to statement and the move statement. So equal to being the entrance, what to code, what to execute, and if it's in the correct state, and then the move being the way to get out of the state to the next state. What they're looking at is a single variable, typically a double integer. In Logix 5000, we'll say, but typically an integer value that is read from and written to chug the program along from state to state with input conditions and output conditions. Obviously, equal statement it allows the rung to execute. The move statement would be getting me out of the rung. In this case, I'm in. Now, granted, the state was it's not matching, so this code would not actually execute, but if it did match, if the sequence was 10 and it matched to 10, I would turn on something and then I would wait for the reaction, move on to the next state. Now, here it is a more appropriate example where the things match. The green feedback has transitioned to state machine. We have an equal statement that we turned on the green command. We got the green feedback. Move to the next state. The next state happens to be check for green and red. Okay, we match. What's going on in this particular line of code? We're waiting for, we can see we have both the red and green feedback, but we're waiting for the timer to time out. The point being, that's what's holding us up and then allowing us to move into the next state. You can also have multiple exit routes. It could be argued that perhaps that statement could be a separate state, but I just wanted to illustrate that, okay, multiple exit routes out of the one state to jump to different points in the program, not necessarily line by line execution. So a couple of hints or tips when dealing with a state machine. Simultaneous multitasking of several states is very easy to implement on the PLC. The key being a different unique state variable. For instance, the representation here in this graphic is that I have not only sequence, but sequence B operating in the same PLC. They might be different functions on the same machine, different axes, different whatever it is. It's easy to implement in a PLC and have them execute their code doing their loops separately. And it can be anywhere within the code so long as it's consistently scanned. When I say constantly scanned, I don't necessarily mean in a continuous task. It could be a periodic task, so on and so forth, just that it's perhaps not condition-based, that things could get skipped over. For instance, maybe the sequence B was somehow in a different task that never actually got scanned, and then we just would hang up. The idea is that it has to be consistently scanned. The simplest way to use a state machine for controlling inputs and outputs would literally to be using the OTE instruction. Turn on the output, wait for the input, move on to the next state. The big drawback to doing this would be if you need to control the outputs from more than one state or more than one module, there's going to be racing in the PLC program as to who would have control over that. And we know it's generally not a good idea to have, actually it doesn't really work that well, to use multiple OTEs to the same output in the same program. So it's highly recommended that we use, if you're turning on discrete inputs discrete outputs, to use latching and unlatching with those outputs. In this case, I'm at state, wait for a state to be in variable 2, turn on the output, get the feedback, move into the next state. If so needed, for instance, if it was an extend, retract on an air cylinder or something like that, unlatch the output before turning on, perhaps the retract, and then wait for the input to move on to the next state. The main tip then is if you get into the off state or a faulted state, realize have a step to unlatch these latches before getting back into your program. Another big takeaway for the self-documentation portion of this, instead of using, as in the previous slide, see individual numbers, instead of doing that, use tags that the tag names are descriptive, and then your code becomes self-documenting. Sequence being, this is our state variable, is it equal to 10, which happens to be turn red on. That is easy for, well, the reason why that's easy for troubleshooting is that I can right click and do a cross reference and see where all is turn red on used or where all turn green on is used, rather than trying to search for the number 10. The number 10 could almost appear anywhere, or number 11, whatever number it is. The point being that tag will take you to the rungs that are using that particular tag in your state machine, and it does self-documentation and makes it easy for troubleshooting purposes. Also use the state, because we can now pump up metadata. We can actually pump these, when I say pump, transfer the HMI can grab the tag names and put them up on the HMI. So if you have, okay, my sequence is now sitting at, in the case, since I have a timer here, it's check for green and red, or something like that. And we can see that sequence through on the HMI. That's another useful idea for using a descriptive tag use for your states. When you do that, create an initialization routine to pre-populate those tags with the appropriate values. So upon startup, move numbers into those individual tags once per startup. In the case, if they get overwritten, perhaps someone is back in the previous screen and they're troubleshooting, trying to manipulate the state, and they happen to put a 12 and turn green on. Well, it'll always revert back to the original values through this initialization routine. When using a state machine, don't, or at least try not to, have your state machine require you to scroll in or zoom out to see all the code. Limit to make multiple simple states are preferred. In other words, do the move, wait for the reaction, move on to the next one, if at all possible. It's just easier for troubleshooting purposes. I'm not saying it wouldn't work, but it's easier for troubleshooting purposes. You can see the entire rung of code rather than having to zoom in and out, perhaps not be able to read because you have to zoom out so far. You have basically a small little program within one particular line on in your code. I know I'm moving a little fast, but questions so far? All right, I'm hearing silence, so I just wanted to prove my point with why to use the state machine. We're going to flip over to I have a VMware image running Logix 5000. A couple of programs, or should say routines, doing different ways of doing the same thing. So here's a traditional bit command, turning outputs green and red on. A state machine doing the same thing. And then control to do that. So what I want to show you is, also this is running, just to give a background, this is running with emulation. So I have Logix Emulate, so it's a soft controller in the background. I'm online with it. Utilizing trending, which is very useful in general, and it's even more useful with motion. For trending, actual position, command position, actual velocity, position error, all sorts of tags, throw it up on a trend, then you can visualize what is happening with your particular axis. So let me enable our bit code to run. We go to bits A, start it running. Produces some arbitrary waveform. It looks like red leads green, different pulse widths, so on and so forth. Okay, that's good. Machine is running. So bits work. Point being, turn this guy off. Go to my state machine. Get up to the top. Still essentially 3 rungs of code. I added extra code to make it a little more savvy or fancy, So we start it up. See the same thing. Red leads green, 2 different pulse widths, so on and so forth. Bits running, everybody happy. Illustration, if I talk back at the PowerPoint, multiple, this was basically screenshots of this routine, multiple exit routes. We can see the sequence number jumping through. It's basically doing a loop from 10 to 30 because of this stop bit not getting me out of the loop. So if we take the stop bit out of the loop, machine stops. I do a clearing of my bits. Now, just to prove a point, this is the bit logic. This is the bit logic, the exact same code, but the order of the rungs has been rearranged. In other words, I moved the timer up above the green command. I'm sure you guys can see that. So let's see what happens there when we enable that to operate. So we put a 20 in. Now we're scanning that. Start the same process. Same code, just happens to be a different order of operations. Oh, wait, we've got some funky pulse width. This is not the correct operation. My green is staying on. I'm doing a faster trigger on my red. Machine is not working. Well, let's stop all that madness. Remember state machine A, green command, red command, this order of operations timer. The state machine B is an exact replicant, except for I have the red command, then I have the timer, then the green command. Order of operations, yet the same state checks. So 2 different ways. The original produced the same waveform as bits A. The second one, fire him up with a different order of scan, not necessarily order of operations, and we get the original waveform. So the point of that is the orderly control of your program regardless of which order the code is executed in. Because the state machine is still sequencing through 10, 20, 30, it's now, oh, well, it's rung 0, then rung 2 does its thing, and then we flip back. Well, excuse me, rung 1, then rung 3, flip back to rung 2. Granted, the PLC is still scanning 0, left to right, top to bottom, but the sequence is keeping it in the order that we want to keep it in the order, the actual execution of it.
So the one thing I'll add in there, Mike, is one of the bullets that Mike had mentioned in the very beginning was about processor upgrades. And just over the years, the Logix has been out for 20 years. L1, for those of us that remember using that processor back in 1999, 2000, obviously was a lot slower than an L8 series processor is today. And over the course of many of the upgrades that we've gotten into the middle of, we've found that by tricks and capabilities that people were able to do with the slow processors don't necessarily, and quote unquote slow, don't necessarily propagate over when you upgrade a machine to an L8 processor today. Whereas if you were using state logic specifically to the motion stuff, right? I mean, there are times when you have to interlock bits and things, but when you do motion, you can actually see machines not quite work the same way with just a faster processor, even keeping all of the logic in the same sequence.
Right, and that's where a state machine would help with that. It's keep it in the same, even though it's in the same sequence, but the state machine can keep you in that state longer, perhaps, or until you can issue the reaction until the reaction happens instead of perhaps blowing through. I mean, it's you can also, granted, hey, we can argue, you can make mistakes with a state machine. You know, I can screw things up many ways as well, but still, the point being, ease of documentation, ease of troubleshooting for others, we'll say, other than yourself, if you're the original programmer. And it's again, with the very conducive to motion. And I want to get back into my presentation. All right. So before I talk about motion in the state machine, we should have a little bit of a review as to what the bits mean and how the motion instructions are executed in Logix. Motion instructions are all transition based. MSO, MSF, I'm assuming some familiarity since you guys signed up for this. MAM, you turn them on, they do their thing. If you turn the rung off, they're still going to do their thing up to whatever. They're still going to complete the process if they can. When I say they, the instruction is going to complete without the rung being live. It's just reiterating the same thing. They do not need to be maintained to operate. So, for instance, an MSO, you do not have to maintain that instruction to keep your servo enabled and holding torque. In general terms, typical instructions, and I'm using MAM because quite honestly, it's probably the most common instruction other than turning a servo on and off or resetting it. You have an enable bit. Enable bit is just a mirror image of the rung preceding the instruction. So if the rung preceding the instruction is true, the enable bit goes true. Plain and simple. The done bit, so there are some misconceptions. The done bit doesn't say that the process you intended to do, in this case would be a move, has completed. It is that the instruction has done all its calculations and it's down in the motion. It's down in the motion planner. Like that's a different part of it's in the basement or something. But anyways, it's in the motion planner, and that whole calculation, it's complete. All the messaging is done. That's what that indicates. There are some instructions that are pure logic functions. For instance, an MRP or a redefined position. That only have status bits being done bits because it's only computational. It's not actually creating motion. So 95 out of 100 times, don't use the done bit to be your transition to your next state. The error bit indicates something's wrong with the instruction or something's wrong with what you're telling it to do. Since I have an MAM up there and the move type happens to be 0, this is an absolute move. The error bit could be set in this scenario if you issue this instruction without the servo being homed, if you issue this instruction without the servo being enabled, so on and so forth, or if you have a value in there that doesn't make any sense, negative jerk or something like that. You'll set an error bit and you'll get an error code in the tag structure. The IP bit, in general terms, means whatever you're telling me to do, I'm currently doing it. it's in process. For instance, in MAM, the command is currently moving. In the case, oh, and actually I have a slide on that. In the case with jog, I'm currently jogging. The process complete bit, that would be your bit more useful for moving on from state to state. So that says, okay, you told me, the controller was told to move axis 1 with an MAM. The command has reached the end position, the process to complete bit comes on. So that the done bit sets after the instruction complete does all its computations and starts executing. The PC bit sets when the initiator process has completed. Everybody following that? Any of these definitions come out of this manual, the reference manual. It goes through the bits, the tags, everything associated, well, not everything, but all the definitions associated with the tags, bits, and structures in motion, logic's motion for AB. So all these bits, potentially, especially the PC bit, could be set from a previous execution. So you have to be careful when you use them. So a low to high transition, the PC bit gets set. That bit will stay set until a catastrophic error or a restart of the controller or something like that on the next time. So you can't necessarily use a PC bit to say I'm in position. You have to use it at the instance afterwards. And you'll see some of that in the next couple of slides. Any of the bits are instantaneously, as soon as the instruction low to high transition, the next execution occurs, these bits are reset. They could theoretically be set again immediately, such as the error bit if the same error condition is there, and it may appear to be that it never goes off, but it does go off for at least one scan. The point is, this is why a state machine is conducive to motion, action and reaction bits built into the instructions themselves. So again, a state machine creates an action, waits for a reaction, built into the motion instruction. I want you to go, tell me when you're done, move on to the next state. Mainly, I guess I should have changed my order or just should have clicked one more time. But anyways, the majority of motion actions, regardless of their path to get there, are moving things from point A to point B, or constantly running, doing a gearing, that type of thing. But we're still moving things from point A to point B. So that's why it's conducive to a state machine. Context-specific help. So even though we have the same bits, they might actually mean slightly different things. But again, they mean the same thing here. MAM, the most important bit, for an MAM, I would say, is the PC, that I've done what you told me to do. In a jog situation, it would be, okay, I'm currently jogging. It's the IP bit. You can have access, and I'm sure the majority of people are aware, you have access to these exact same screenshots through the help files, which have gotten better in version 31 and up. Not that they were bad before. Okay, now it's doing it. Anyways, highlight your instruction and press F1. And then everything you need to know about an MAM comes up and is available to you. So just remember that. Highlight your instruction, press F1. And that actually applies to anything in Logix for the help files. But point is, this is that exact same table talking about the bits. Previous to that would be the different functions of an MAM instruction, which is outside, or the different arguments for an MAM instruction, which is outside of the context of this conversation here. We can always talk about that offline. But I just wanted to show you that that was available to you. Yep. So it's basic state machine for motion. Equal statement, hey, I got to, let's see, is it equal to unload or move to dump position? Yes, it is. I mean, not necessarily in this state, this case, but yes, it is. do the motion, wait for the process complete bit, move on to the next state. As a side note, ideally all your parameters, even though they can be hard-coded, when I say parameters, in this case it would be speed, acceleration, deceleration, position. It would be in tags that could allow you to populate them from a recipe or be adjusted from an HMI. When doing motion, because of this phenomenon that the previous execution, some bits could be maintained, it would be incorrect to set up your logic as is shown in the first screenshot. Yes, I'm in the state. The permissive may not be true when I get there, and I may have a PC bit, a process complete bit, set from the previous execution. So what would happen if this is not ready? I would just come down through, blow through it, never do this action, and move on to the next state. It's okay or better to put the permissive out for the entire, we'll say the entire reaction and entire action and reaction portion of the instruction. Here we see the same repeat of what's okay, but even better might be to keep it, I said earlier in the presentation, one state, one action, following the same one decision per state rule. Put the permissive in a state, then move on to the motion, so that it stays and waits in that state until whatever this permissive may be, the loader is full or something like that. Taking it yet another step further would be to throw in a watchdog or a wait timer of sorts into your code. So we're out here, we're waiting for the thing that we have to happen. Built into the code, we have at each rung, we have a watchdog timer that starts timing as soon as we get into the state. If the permissive is made, we move on. If not, create a fault, move it to the off position and announce it on the HMI so they can troubleshoot just the thing associated with what it was telling it to do. Maybe the loader was not being full, or the proc switch cable had been stepped on and broken, or whatever that is. This might be the best way to manage your state machine for troubleshooting purposes and prevent people from calling you.
Mike, what about if you go back one slide in the control words, which is your dones, your process completes, what about unlatching them independent of the instruction? What's your advice there?
Oh, okay. Good thing Sean asked that. I didn't actually cover it. Do not unlatch bits. So please do not unlatch these bits. The state machine helps you deal with how they react. Do not unlatch. It can create funky actions. Just because you unlatch the bit doesn't mean internally to the instruction that it thinks the bit is latched. So point being, use them when appropriate. Do the action, wait for the reaction. Now after this point, that PC bit is no longer valid for anything else, because I moved on to something else. It could have been the next state. It could have been move it back to the load position. This PC bit would still remain set, but now we have a new PC bit, process complete. I keep saying PC bit. We have a new process complete, and that means something within the context of this instruction. Once it's out of that state, it's no longer valid. So a false to true transition then creates the instance for a valid PC bit. Do not unlatch bits as part of your control. That's my advice. So a little bit of review. Motion is very conducive to a state machine. Action and reaction is built into the instruction. State machine can keep code executing in an orderly fashion. Be self-documenting. Provide ease of troubleshooting from one engineer to another. With thorough programming, such as the watchdog timer, keep a machine in a state until your reaction is met or until the watchdog times out, and then we have enunciation on an HMI. One thing I didn't cover specifically was easier expansion of the code. For instance, if I wanted to, this literally just create this particular little sample of code, creates some motion. I'm trending on the green line. I'm trending the actual velocity of a virtual axis. I'm trending the actual position in the blue line of a virtual axis. And then I'm just saying, okay, end the motion after that. If I wanted to, I just create another state to have it do something else. For instance, let's see. We could have this, instead of ending the motion, let's do a return to start. So now it'll do an incremental move. Of 100 out, but then go back to 0 and then stop the sequence. So another side note, take advantage of trending. Any of the axis data for illustrative, for visual purposes is highly recommended that you get. If you're not familiar with trending, get familiar with trending. That's pretty much what I have for today.
All right, thanks, Mike. So with that, we will wrap up. So I want to thank everybody for tuning in today. If you do have any questions, obviously any of the Rumsey specialists are available for helping to answer them. But feel free to reach out to Mike directly. You know, we will be continuing to host the Tech Talks every Tuesday and Thursday, at least through the end of May. And if you need to see what's coming up between now and the end of May, feel free to go to the Rumsey website and take a look under our upcoming WebExes and webinars, and make sure to log in. So with that, we will sign off. I appreciate everybody's time.